Hello, everyone. So this is Bob, Chandler, and Diego talking about PGO and LLVM.
All right, good afternoon. I'm Bob, and together with Diego and Chandler, I'm going to talk about PGO and LLVM. So PGO is profile-guided optimization. The idea is to run an application with profiling to collect a sample of the behavior of that application, and then come back and recompile it with the profile as feedback so the compiler can make better choices about how to optimize. What's in that profile? Well, it could be a lot of things. The typical thing and the place we're starting with is information about the control flow, particularly the execution counts of the code. But in the future, we could extend this to include things like type information or even values. What's it good for? I'm just going to give a few examples. Chandler's going to talk later in more detail. The code generator can lay out the basic blocks in the order that they're most frequently executed. So this gives you better cache behavior and also avoids the overhead of branches. The register allocator can place spills in infrequently executed code. The inliner can prioritize the most important function calls. And we can add completely new optimizations like hot and cold partitioning, where we put all the hot code in one area of the address space and all the cold code in another area, so we can reduce the size of the working set and improve the paging. So taken together, these and other optimizations can give significant performance improvements. But of course, there's a catch. There's always a catch. PGO is based on the assumption that you can predict the behavior of a program. And in a lot of cases, that may be true. If it's not, it can actually make your performance worse. If you profile the application with inputs that make the program behave in one way, and then optimize for that, and then later come back with a different set of inputs, it may actually hurt. So when you use PGO, if you choose to do that, you have to be very careful to think about training the optimizations by collecting profiles that are representative of all of the different ways that you care about performance. One other catch is less significant, but depending on how you do PGO, there may be some overhead in terms of how you build the application. I want to give just a brief history of PGO and LLVM. This is in the spirit of Chris's talk this morning, but less detailed. Going way back to 2004, Chris added the basic support for instrumentation, collecting that into profile information, and there was even a basic block placement optimization using that information. And it kind of sat there for a long time and didn't get used much. A few years ago, Jakub Stazik added the core infrastructure that we're using now for branch weight metadata, and then the computation using the metadata to compute the block frequencies. We wired that up to a few different optimizations, most notably the current block placement algorithm that Chandler implemented. And then just last summer, Alistair Murray did a summer project where he used the old instrumentation code to feed back in and add the branch weight metadata and drive all these optimizations. So at that point, we had a complete end-to-end PGO build flow. But it wasn't productized, and it was certainly not easy to use. So that brings us to today. Here's an outline for the talk. I'm going to talk first about a new approach to doing a different kind of instrumentation in the front end. And then Diego's going to come up and do an alternative approach that uses sampling. And finally, Chandler's going to talk about how the compiler can actually use this information that we're collecting. So on to instrumentation. The approach that I'm going to describe here has some trade-offs. There's, like any engineering challenge, there's always some trade-offs. Here are the advantages, as I see it, of this approach. First of all, it gives very detailed information. We're going to collect instrumentation for the execution counts of all of the code. It's very predictable. Unlike an approach with sampling, as Diego's going to describe, as long as you have the same environment and the same inputs, you'll collect the same profile every single time. And this also gives us a framework to make the PGO process more resilient against changes. And I'll talk about that in a minute. The disadvantages of this approach are overhead. That instrumentation requires one kind of overhead. First, you have to build your application with the instrumentation, and then you have to run it, and because there's all this instrumentation, it's going to run more slowly than it normally would. So here are 4 design goals that we set out to meet with this implementation. And I'm just going to go through these quickly up front, and then I'll talk about them each in more detail. First of all, we want it to degrade gracefully when the code changes. We don't want the profile data to be tied to any specific compiler version. We want to minimize the instrumentation overhead. I'm not even going to come back to that one because I think it goes without saying. And finally, we want to be able to accurately map these execution counts back to the source. So those are 4 goals. Let's start going through those a little bit more in depth with how we deal with change. And the first scenario we care about here is where I've collected profile data, and then I found a bug in my code, and I fixed the bug. Well, it might take quite a long time to go and reprofile with that change, particularly if you have a large set of inputs to cover all of the cases you care about. So we want to be able to fix the bug and still use the old profile data. But in some cases, the bug fix may render that profile invalid or too difficult to use. So the idea that we're going to do to start, at least, is if a function has changed in a way that we can't use the profile, we may have to ignore the profile data for that function. But all of the other functions, we want to continue to work with the profile feedback. There are some changes that are OK. If I modify a function in a way that changes the control flow, so the execution counts are different, that's a problem. If I just change it in a way that changes the value that's assigned by a particular assignment, normally that would be OK. So we can distinguish between different kinds of changes to a function. So there's another kind of change that's also really important, and that's compiler changes. If I'm a developer and I've collected a set of profiles that I think are representative, I've got my code building and optimizing and it's all working well, and then I upgrade to a newer compiler, the last thing I would ever want would be for it to get slower. The new compiler should always make things better. But if the profile data is somehow tied to a version of the compiler, it could be worse, and we really want to avoid that. The last thing you'd want with a compiler update is to get a build failure or a performance regression because some of the profile was just silently ignored. The instrumentation that we had in LLVM before was tied to the LLVM IR. And it's not uncommon for the IR generated by the front end to change over time. Usually not in large ways, but sometimes the IR generated will be significantly different. And so if we associate the profile data with the structure of the IR, this gives us a problem if we want to upgrade the compiler. And my last design goal, I'm just assuming you all agree with me that minimizing overhead is good. The last one is the source level accuracy. And the issue here is we want to be able to use the same profile for code coverage. It would be unfortunate if we had to have 2 completely separate styles of instrumentation, one to be used for code coverage and another for PGO. And so what that means is that code coverage needs to accurately port back to the developer at the source level what code was executed. And so if we're going to use the same format for PGO as we do for code coverage, then our PGO instrumentation also has to be able to map back accurately to the source. So those are the design goals. How can we come up with a solution to these problems? And the idea is to use the source. If the instrumentation and the execution counts are tied to particular constructs at the source level, then that solves our problems. The Clang ASTs map more or less directly to the source. So even though various details in the ASTs or in the structure of the front end may change, that basic correspondence of source to ASTs is going to be the same at the level that we need. at least in almost all the cases that we expect to have come up. So if we record execution counts for particular AST constructs, we'll be able to continue to use profiles as the compiler changes. This also gives us a framework where we can detect changes in the source in a very accurate way because we're looking directly at the ASTs and not at this intermediate IR that has other dependencies. And finally, the instrumentation is now independent of optimizations and debug info. We can get the same results whether we have debug info enabled and whether we optimize or not. So I just want to walk through with an example how this works. The compiler will walk through the ASTs in program order and assign counters for the instrumentation to particular control flow constructs. During the PGO phase, when we're reading a profile back in, we'll walk through the ASTs in the same way. And the minimal check is if the number of counters are the same in the current AST versus what's in the profile file, we know how to map them up, to match them up. Of course, it's possible that the code has changed in a way where that really might not be the right mapping, but that's kind of the minimum level at which we can make sense of the profile data. And to make this more accurate, to detect changes in the code, we intend to experiment with putting various kinds of hashes of information in the ASTs into the profile data so we can more accurately detect when the code has changed and report that back to the user. So here's an example, just showing a simple AST. So a while loop with an if-then inside of it. And so we're going to walk through this AST and assign a counter C0 for the beginning of the code. We go down to the while loop, and we have 3 more counters, C1 for the condition, C2 for the body, and C3 is for exits from the loop. And then we go down inside the if-then and put a counter C4 on that then block to record how many times the if condition is true. We'd like to minimize the overhead, though, and not every block needs a counter. If you have a traditional instrumentation, as GCC does for GCOV profiling, they compute a spanning tree of the control flow graph to compute a minimal set of edges where they need counters. Because we're doing this based on ASTs instead of control flow graph, we can't use that same approach. But because there's structured control flow, we can often get the same benefits just by taking advantage of the structure. And here's an example of that. Similar thing, just a compound statement with an if statement and another statement after it. C0 at the beginning. For the if, we only need a counter C1 on the then block because the else block can be computed as C0 minus C1. The other statement after the if also doesn't need a separate counter because we know it's also going to execute C0 times. And we're currently looking at seeing if we can find a way to also be smarter about minimizing the number of counters that we use for loops. I'm going to skip that for the sake of time and go right to the numbers. We've got a prototype of this. We're working on getting it cleaned up and submitted as a patch for Clang. But we've been able to get it working and compile some spec programs and measure the overhead, both in compile time, because there's all these counters in the code, it takes longer to compile, and also in execution time, which I'll show on the next slide. I'm comparing here to the GCOV style profiling in LLVM, which does not do the spanning tree optimization. So it's putting counters all over the place. You can see the overheads with the GCOV profiling are 50%, 60% of extra compile time. Whereas with this new PGO style profiling, the numbers are much smaller, in the 10 to 30% range. Some of them are higher, but still much faster. Here's the overhead for the execution time. And again, we're much, much faster than the GCOV profiling that we have currently in LLVM. So there is still some significant overhead on all of these. That is an inherent cost of doing instrumentation. And so now Diego's going to talk about an alternative that can avoid that overhead.
Thank you. So the alternative is to be completely lazy about instrumentation and not do it at all. The idea is to take advantage of tools that people already use for human analysis. When you want to find out what your program is behaving, what's the optimization pattern in your program, you run it under an external profiler. Perf, O-profile, in the Mac world, there's Shark or instruments. And it tells you, the external profiler will tell you what the program is doing, what are the expensive parts, what percentage of the time is spent where. So the idea is, why not use this external profile data as input to the compiler, the ultimate analysis machine? So here's an example. You run this program under perf, and it tells you that 66% of the time is spent inside that loop. Well, of course, it's just the one loop, but it has that information. So instead of instrumenting your code, the idea is to that data that the external profiler collected about your program, feed it back to the compiler. And the reason why we need an external, or we want an external profiler, it's simply because we save ourselves the effort of doing the instrumented builds. So the user does not have to have a special build where they build an instrumented version of the program, and then they need to run it under special trainings. So there's no build time overhead. All the build time that Bob was talking about is gone. The runtime overhead is also almost gone. Nowadays, profilers, especially sample-based profilers that will use hardware counters, are very low overhead. So you can have the profile always on, meaning that your profiles can be collected in production environments. Your profile data is, shall we say, perfect, because it was collected while your program was running in production. And you don't need to do any training. You just run your program. And next time you compile it, the data that it collected during its production run is used as input to the optimizer. It also allows to use any kind of profiling. It does not depend on the compiler. If you have a game engine and your game engine has a profiling component that gives you data that you can use in the optimizers, anything. It doesn't matter what it is. It could be value profiling. It could be samples from your game that are very specific to your application. Anything you can convert back into hints into the optimizer can be used. So the user model is greatly simplified. At the top, you have the source code and the regular build with O2 that generates the binary that is used in production under the profiler. The profiler will generate data that then you can feed back into the optimizer to generate what we call the peak optimized, because it'll use the data that was collected there. You'll see that one of the things we add here is a -G option, especially under sampling, because what we want to do when the profiler runs, the profiler gives you PC displacements, instruction addresses. Those instruction addresses, we want to map it to something that the compiler can make sense of. And that something is source and line number information. So from the external data from the profiler, we convert it into line number information and function names. So we need to reread the binary to pick up the mangle names from the binary, pick up the PC addresses, convert them into logs, into source logs, and then we can feed that into the compiler. This process, as you can imagine, is going to be lossier. We lose precision. That's the main trade-off that you have in this design. You're going to lose profiling this precision, particularly if you're sampling every other second. You've lost the game. But it will be very lossy depending on what you're doing. However, no amount of badness in the profile will affect the correctness of the program, because the compiler will either find the mapping from the samples into the code or not. It will only affect performance. Sometimes it'll affect performance tremendously badly, but that's the price you pay. A scalar pass will take that profile, put it into the IR, mapped according to the source locations, and it will feed it into the analysis API so that when the optimizers are querying the analyzer about branch weights, any other kind of cost model they may have, the analyzer will automatically use the profiling data. Currently, we have an implementation using Linux perf that takes the sample-based profiles, converts it into a format that LLVM can read. The scalar pass that I wrote converts these samples into branch weights, and then the analysis routines use it, so we generate this IR metadata for branch weights, and then the optimizers, Chandler will tell you which optimizers use them. I know that some of them use them because I grabbed for the metadata and I saw it in various parts of the compiler. However, as I'll show you shortly, more work is needed here because it's not all good. What limitations you have when you use this kind of profiling? The behavior of your program, and this is shared with instrumented-based profiling, must match the profile. If you have a stale profile, your performance will degrade, sometimes significantly. You can mislead the optimizers, because say you had a code that had this built-in expect for x greater than 100, but every time you call it, you're calling it with values less than 100. So what you expected to be hot is actually cold. So you lied to the optimizers with your built-in expect. And the profiler will say that. So now what do? Do we believe the profile, or do we believe the source code annotation? Do we warn the user? Do we overwrite the built-in expect that we found? It's actually an interesting question, because if you overwrite the user, you may degrade performance because you may have just a bad profile, right? And but it may be that the user doesn't know what built-in expect really does, right? So it's a question that we still haven't answered. Sorry? A warning. If I could generate warnings from LLVM, that'd be awesome, but I can't. I found out that I can either die or silently do nothing. Die is good. Right. Another restriction or another problem that you may find using this approach. Remember, from the PC instruction, I get the line number and the file. But I may have a single line with mini-CFG inside of it. So if the profile says line 2 is hot, it doesn't help me, right? Because I've got a branch here. Which part of the branch is hot? It hasn't told me. So column information can be used to distinguish when I read from the binary, the column information I pick from the dwarf, I can say, oh, okay, so column whatever, 10 here is hot. Sometimes column information is actually not sufficient, particularly when the compiler decided to open code something. So you may have a mini control flow graph with cold and hot paths in the same line and column number. So to begin with, you need good line table information. So when the profile is bad, if the dwarf info, debug info is bad, then you're going to have this problem. And of course, the optimizers must use the profile. In our experience at Google, we found that the inliner is probably the most important optimization you can do, particularly in this kind of profiles that you get cross-module information. Out of a sample profile, you will get functions that are in different files. So this will give you cross-module inlining hints that you can use. These are early results on SpecInt. I don't care too much about the actual numbers, but sort of the shape. The green ones are Google's GCC version, latest version, using the sample profiles. Higher bars are better performance. And these orange bars are the LLVM version of the profile. Sometimes it's good, like here. Most of the time, not so good. It actually, and the blue bars is baseline O2 performance on LLVM. This is not on scale, guys. There's no zeros here. The differences are actually 2 to 7%, so don't read too much into the height of these bars. But you see that sometimes profiling is even worse than O2. And that's bad. And that's something that it's actually hard to fight against. SpecFP is kind of similar, except for some reason LLVM seems to do a bit better on floating point with profile. So now Chandler will tell us what we need to fix to make profiling always good. Status. I think, sorry, Chandler, I've forgotten about this. As I said, there's a perf-based implementation. It right now works with flat profiles. This tool that converts perf, we're working on releasing it, and the patches are going to be in trunk as soon as the review is over. And there's a bunch of stuff that next follow logical steps, like adding function attributes when you find a called function. The encoding of the profiles is a little bit inefficient now because it's a text file. And also adding context-aware profiles instead of just flat profiles. And now Chandler is going to tell us what we do with these. So.
Thanks, Diego. All right, so with that, I'm going to hopefully talk to you guys a little bit about what the optimizer does with all of this profile information. The first thing I want to kind of clarify is that I hope you guys were paying attention to those numbers, because this was my face when Diego showed me these numbers. Hopefully. I was really surprised by how bad LLVM got when we added a profile to it. And I think part of the problem is that profiling in LLVM is still really new, and there's still a lot of confusion around exactly how it works. A lot of people get into profiling and they feel a bit like Homer. And I think we can do better about actually explaining exactly how the infrastructure is supposed to work. And so I'm going to try and give an overview of all of the infrastructure that we use for profiling within LLVM. So Diego and Bob both talked about how we can get IR annotations into LLVM, which represent some profile, right? We've been able to take source code annotations for a while. Bob was talking about instrumentation coming in. There's also, sample profiles coming in. But eventually, all of these things end up coming together inside of the IR, inside of kind of IR-based annotations. The rest of it is LLVM's responsibility as an optimizer. We need to take it through an analysis, which helps us understand the profile data that we have, and then we need to move it through optimization passes. All of the optimization passes always access profile information through an analysis pass. This is really convenient because it means there's one source of truth about what a profile means, or what your optimization pass should be doing with a particular profile. And that helps you actually get the right answer. It helps actually address some of the questions that Diego raised, and it's probably where a lot of the work's going to go into in order to not have profiles actually hurt performance. So So this analysis pass is called branch probability info, all right? And you can kind of figure out what it's doing, right? It takes some basic block, right? And it goes to its various successors, and it says, there's this one edge right here that's hot, right? And the way it represents this is as relative probabilities between the various successors of a particular basic block. All of the probabilities sum to 1. We represent them as nice kind of stable integer ratios. There's no floating point math. We want the math behind this to be really solid. It's not 100% yet. It's not entirely correct, but it's getting better. And we want it to be nice and portable and predictable. So what this is actually how this actually looks like an IR looks something like this, right? You have your IR, you have a branch around a true block and a false block, and you have this little hint up here, this profile marker. And that refers down to some metadata, which is really verbose in text, but it works out pretty well in the actual IR. And it says that there's a weight on one side and a weight on another. Now, if you're thinking about this, you might notice something right off the bat. Which is 64 and which is 4? This is one of the most confusing parts about the metadata. It actually is tied to the order of the targets of the branch instruction. So because we go to T first and F second, T gets 64, F gets 4. This will come back to haunt us. Okay, so we have branch probability info. It's this nice analysis pass. It's going to take this profile information, right? It's going to pull it together with stuff like all kinds of other information. It's going to build this kind of graph. We've got a hot edge here. We have a loop back edge. Branch probability info is really nice. It understands the structure of the control flow graph. It can synthesize probabilities based on it. It doesn't need a profile to know that most loops do in fact loop, right? And so the back edge has a tendency to be hot. It understands a lot of those properties. And it even could understand kind of interesting things that might contradict a profile. So here we have a profile, right, which is lying to us. This isn't the user line, this is the profile line. We have a profile. It says that we're very likely to go to true, to this true basic block. But true terminates at unreachable, right? And that means that we're never going to reach it. Somewhere before this unreachable, inside of true, we have an abort call or some other kind of error handling, right? And we collected a profile on a program that was actually hitting its error path every time in the profiler. And branch probability info can correct for that, right? Even if you have error paths that become hot for some dynamic reason, we actually understand the structure here. We can get back to a real profile. There's a lot of other nice structural properties of the IR that we understand. So if you have a call to a cold calling convention function, right? We know that calls to those are not in hot paths, and we can actually synthesize the correct probabilities for that. So just like we used metadata when we had a profile coming from an input, right? We can actually use the IR itself. We see this cold call, right? We understand that this basic block can't be hot anymore. Okay. The final thing we do is we have a set of heuristics, and these are really used to kind of plug the gaps in any profile data we have. If there isn't actual profile data from some profiling source, if there isn't a source code annotation, if there's not an inherent structural property of the IR that tells us what the probabilities should look like, we use some basic heuristics, such as whether or not you're comparing a value against 0 or against -1. There are a bunch of kind of common cases that we try to handle. All right. So there are a bunch of these. I think the most interesting one is actually this one. This one tends to be the most useful static heuristic that we have in the entire thing. We're noting that you're comparing a pointer against null, right? And it turns out that statistically speaking, most of the comparisons against null are false. And so we actually appropriately weight those edges that way. And this will be kind of controversial because a lot of people think no, the fast path is when it's null and you can just bail right out of the function. And as far as we can tell, the static heuristics which were published in a bunch of papers are correct, and you actually want to bias toward the non-null path in the program. All right. So this is what branch probability info is telling us, and I've given us a little bit more context. We've got like an entry block at the top of the function, right? It's giving us these edge weights, right? We understand that some of these edges are hot, some of them are not particularly hot, right? The probability info is telling us that. Some of these edges are the only edge in the graph, and so they don't matter. They don't have a probability, right? Of course you're going to take that edge. But we need something that gives us a little bit more context. And for that, we use an analysis called block frequency info. And this essentially maps the probabilities for each edge across the basic blocks of the function. And this gives you function relative frequency for every basic block in your function, right? So if you have an entry block, right, the entry block is the one that doesn't matter because we just assume some fixed baseline for every function, and then we give relative to the entry block weights to each basic block in the function. What this really lets you do is it lets you contextualize the information you got from branch probability info. For example, this switch block is actually hot because it's the target of the back edge of a loop. Because the switch block is hot and there's a particularly hot edge coming out of the switch block, this hot edge is a lot more important than other hot edges in the function might be, right? So we want to contextualize the block local branch probability by the function-specific block frequency info. Making some sense here? All right. So what about MI? Because we have IR, and that's really wonderful, but a bunch of profiling-specific optimization passes actually operate at the MI layer. We actually map all of the IR stuff into MI. It does lose a little bit of accuracy. We use the back references to do it. We don't recompute the profile information, but it is available, and we actually are using it today. So some other interesting things to talk about is resolving conflicts when you have some profile information that says one thing, other profile information says something else. The most interesting case is actually when the profiles are incompatible, right? When you have a profile that says there is a hot path through the function, which simply cannot be hot. And we need to be really cautious when we're actually trying to resolve this, because as Diego pointed out, sometimes the programmer is lying to you. And in other cases, we've seen the actual profiles lie, or the debug information lead to the profiles being wildly inaccurate, or to the optimizer actually changing the structure of the program so much that what the profiler measured doesn't reflect the behavior that the program's going to have when it's executed. So this is an ongoing problem we have, and it's really handled in the analysis phase. We don't want each optimization pass to figure out how to resolve these conflicts. So the analysis is responsible for all of the conflict resolution, for providing a unified interface to this kind of information inside of LLVM. Then we get to the really hard part of the analysis and all of the information about profile information in LLVM, cache invalidation. So what happens when you have an optimization pass and it transforms the control flow graph in a way that makes the profile annotations that Diego or Bob's work have added to LLVM no longer accurate, when it changes the meaning of that profile information? This gets really, really complex. So here's kind of the example that I'm going to use. This is the same example I started off with, right? We have a simple branch, we have some profile information, we think that we're going to go down the true path, not the false path, right? Nothing too fancy here. But there are a bunch of optimization passes which will actually reverse those operands, right? They'll reverse the operands of the branch, and we have to remember every single time to reverse the operands of the metadata node at the same time. We've gotten this wrong at least 5 different times in LLVM, and every time you don't just get no profile information, you literally get the reverse of what the profile information told you to do. It's really, really frustrating. And it also tends to be phase ordering sensitive, and so it can be hard to even reproduce this. Okay, so that's a fairly simple one. Sometimes, though, we start with our basic example, and we get a different transformation. We get something like this. We're able to speculate all of the interesting things that went into a phi node coming out of the bottom of our actual function, right? And when we speculate it behind a select, we have nowhere to put the profile information. Like, we have profile information, it's still attached to this control flow graph, but the next optimization pass we run, which can nuke the control flow graph, is going to nuke all of these branches, all of these edges, and the metadata associated with it, and all of our profile information is gone. If we ever decide, maybe we didn't want to speculate that, we can't recover the profile information. We have no actual way to recover this. And so this is one place where LLVM, even today, loses information about the execution properties. Another example, this one is a little bit more complex, but this one is actually the one that is, I think, most frustrating. So in this one, we've got 2 comparisons, right? We're taking, and then we branch on them. And for some reason, we've got some profile information that says we happen to think that this is usually true. But maybe actually computing this comparison is way more complex than the one instruction I've got up here, because I'm trying to make it fit on a slide. And LLVM actually decides it would be much cheaper to only compute the second half of the comparison if we need it. Right? So we can do that, right? We can first compute the first half, branch, then we can compute the second half, branch, right? And we've added a new layer to the control flow. Where does the profile information belong? Right? We don't know what part of that original condition was actually likely or unlikely. We have no way to reconstruct this, right? If we leave the profile information alone, it's going to be wrong. If we duplicate it, it's going to be wrong. If we remove it entirely, well, it won't be wrong, but now it won't help us any. And LLVM actually does this optimization a lot in Simplify CFG. We've taken, I think, 3 attempts at fixing this. I think that there's still a few bugs with it. I don't think we've completely nailed it down, essentially trying to distribute the probabilities evenly across the synthesized branches, but it doesn't really work well, right? So this is again, a fundamental limitation. All right. Some other things that we think are probably going to become increasingly relevant. Do we need other annotations, right? Do we need more information? Right now we have a few, but we don't have as many as we think we need, especially as we get more interesting parts of profiling. So with that, I want to switch over and talk about profile-guided transforms. I'm not actually going to talk as much about this, though, because frankly, we don't have very many. So we've got one which is really nice, but which I actually know very little about, and that's spill placement. Jacob, I see him here, can answer the real questions about this. But the idea is that the registry allocator has to do tie breaking between what it's going to spill onto the stack, and when it's doing that tie breaking, it can actually consider where the spill gets placed. And if you can place spills into the cold path, that's unsurprisingly better than spilling in the hot path of a function. And so we can use profile information to do a better job at spill placement in the registry allocator. And we do some of this today already. You can also do code layout. And this is actually one of the kind of classical uses of profile information, and one of the more important ones. And this is one place where LLVM is really good today. We have really good code layout optimizations that use profiling pretty well. It's called machine block placement. The way our code layout works is it runs at the very end of the MI passes. It does a CFG-based code layout first, and almost all of the layout rules are control flow-based. It only uses profile information for 2 things: to break the kind of inherent ties in any kind of diamond structure of a control flow graph, and to take very cold regions of code, hoist them completely out of the function, and to tack them on at the end so that we have relatively nice hot regions at the top of each function. And so far we're seeing good results from this. This one seems to be working pretty well when we have good profile information. But we can do a lot better here. So these are just some ideas. These are things that people have done in other compilers and things that we think are important for LLVM. One is hot-cold partitioning, which actually takes it one step further from just code layout. When you have a region of cold code at the backside of a function, it would be better to actually let the linker sort all of those function halves to the very back of your binary, so that even as you call between functions, you still don't pay the cost of the cold code. The inliner doesn't even know that profile information exists. I've talked about this before. It's a really, really big problem with LLVM's infrastructure and one we have to solve. However, it's not clear how much this is going to help. It's going to help in specific situations, but LLVM's inliner is primarily focused on simplifications, not some kind of call overhead reduction inlining, and so it's not clear exactly how much of an impact this is going to have. But there are other things we can do that are kind of like inlining. Things like outlining of cold code regions into their own functions, merging cold code into one function so that we can save on the binary space, and lots of other kind of aggressive interprocedural optimizations where we can move around cold code and get it out of the way of the hot path of the program. And all of these are going to likely take a really, really big impact. So with that, I want to summarize kind of where we are with PGO, right? We have strong analysis support in LLVM from the annotations down. We have some problems there, but we have a pretty good grasp on it. It's probably the most mature part of profiling PGO and LLVM. We have 2 kind of parallel and complementary efforts to bring annotations into the IR from different profile sources. We also have the most basic of the profile-guided transformations in LLVM already. But there is still a lot of work to do to actually use profile information more aggressively throughout the entire optimization pipeline. So with that, I think we're to questions. Do we have time for questions? Yeah. Excellent. And Diego and Bob, you guys actually have to come back up here because I'm not going to answer all of these.
I know I know some recent work was done in order to be able to do source code debugging of LLVM IR. And so what I wondered was whether it would make more sense to tie the profile back to optimized LLVM IR as in those debug locations. Would that possibly sidestep some of the issues?
You mean for sample profiling? We only need line table information. You don't need full debug info. As long as the instructions can be mapped to a source lock, you're fine. Then you can map it into the IR. Not sure I'm following the question though.
My point is, if part of the problem is being able to maintain profile information in the presence of optimizations, why not actually tie profile information to optimized LLVM IR, where the source code location is instead of being a source code location in the original C source is an LLVM IR location?
Well, one kind of basic problem with that is if you tie the profile information to the optimized IR location, then you can't load the profile and use it until you finish optimizing.
Right.
And that means that we didn't get to optimize based on the profile.
So actually, I was kind of going to agree with, I sort of had the same comment. So I don't really understand why we need to have metadata. I mean, it seems like it causes so many problems. It gets disconnected from everything else. It creates all the problems with the debugger. So it seems to me like you ought to just get rid of that and merge it into the IR somehow. Then you can keep all this stuff together. It seems like it's causing various problems by keeping this separate metadata area.
Okay, so first off, metadata is in the IR. And second off, well, I'm not the world's biggest fan of metadata. I don't want this to be a metadata talk, so maybe...
Nobody is.
Well, you could...
Punt.
I will say one thing. Sorry. In GCC. So in GCC, this metadata is kept in the actual CFG. So it's never part of the IR. When you do a flow, control flow manipulations, it gets moved naturally because it's placed on the edges or the basic blocks. But if you do have the metadata, you have to transform it.
So I will just add that I haven't seen the use of metadata be a problem at all for this. So it seems to be working just fine for us. But the fact that it's metadata doesn't matter. It's keeping the information up to date, and it doesn't matter where the information is stored. Keeping it up to date is the challenge.
Right, because even if you keep it on the CFG, you have to, when you do a transformation. Yeah. One of the transformations that when Chandler said when we split this predicate, you have the same problem if you do it on the CFG. Or if you decide to predicate something and then you say, oh no, I changed my mind, you've lost the CFG. So yeah, it's same problem.
So I'm interested in doing profile-guided loop trip count estimation. And so I'd like to know if any of the current infrastructure can be used for that, and if not, what would need to be enhanced or changed in order to make that possible.
What do you mean when you say estimation?
Well, okay, so I mean,
because we're actually measuring the loop trip counts.
If you're instrumenting, I could say I could count the loop, I could count the loop iterations. If you're sampling, I assume that implies some kind of estimation.
Well, if you're sampling, you get fuzzy numbers that are relative to each other. So all you can do is compare them. This edge got 10,000 samples.
So,
but
I think that you have the information you would need to do this in the block frequency. I mean, it's going to be a little bit tricky to interpret it correctly. You're going to have to be very cautious. But if you look at the loop headers block frequency and you look at the block that feeds into the loop, that relative frequency is going to be a rough estimation of trip count.
So I mean, is there a relationship between that and say the cost? Like, could I do a cost estimation on the block? Say like, how long it would?
It won't tell you how many times the loop executed.
But the numbers are scaled, right?
Yes.
Okay.
Right.
So the relative frequencies will be meaningful for understanding whether the loop executes many times relative to the function being called versus few times.
Right.
Cool.
Or to the outer loop, which is the more common.
To build on the first question, where you mentioned that you couldn't put these annotations inside the IR because then you would be after the opt already. Could you put them in there post-opt and then rerun the optimization?
Several of the optimizations are not information preserving. And so once you run them, you've lost a key element. So as an example, if you wanted to use loop trip information to understand when to vectorize loops, right, you're going to have to instrument before you vectorize the loop and read it back in then. And we can keep making arguments up through each step of the optimizer. As soon as you make the argument at the inliner, you've essentially given up. So.
I had a question about, it seems like most of the profiling, the counts, the front-end profiling counted blocks, and the profiler, the sampling-based one actually counts time. But the optimizers seem to look at the data of like, what was the probability of taking a given edge. In general, that can't actually be computed from either of the other ones. And so like, one, is there edge profiling?
So with the front-end instrumentation that we're doing, in many of the cases, you can put the counters on the blocks and then calculate the edge counts from that. There are some cases, particularly with switch statements, where we actually have to insert the counters on the edge to get the correct information.
Good, okay.
Specifically about select, why can't you put a branch probability on a select? I understand that it's not something you can measure, but it's something the optimizer could preserve.
What do you mean you can't put it on it?
Well, I think you were saying that when somebody was saying when simplify CFG turns a diamond into a select.
No, it's not when it turns it into a select. You mean just a select. You can put the profile information on it, we just haven't done that yet.
Okay, so that's just something missing. The other thing is if you have a highly biased branch, it's probably not a good idea to turn it into a select. And that's not exactly the most awesome part of the compiler.
So specifically,
heuristics, so using profiling would be probably a really good idea.
Well, so Benjamin looked at this, and what he really wants to do is he wants to go ahead and form the select, but to keep the metadata on it, and then in the back end, when we understand register pressure and such, feed this information into both if conversion and a reversed if conversion to move it back and forth appropriately for whatever the profile says.
I don't know if I state the obvious. I've heard that comparison many times, that you're trying to recreate a cow from the sausage when you try to feed information up in the flow after the optimization. So, okay, maybe two pass with -0, collect information, feed it up with almost no optimization, keep it on a high level, as close to C or whatever the source language you can. And that way you obtain some skeletal information that's unlikely to change and that represents the general flow of the code that's later on being reinterpreted by optimizations and being sliced and diced.
Sure. Training, if you train with 0, usually you get slightly better with sample profile.
Better correlation, right?
Right?
But then you go and optimize with 02 and 03 based on that skeletal information, and that still be better than being totally confused.
Right,
so, but at that point you're doing 2 builds, and you lose the advantage of having to
right.
Users understand that, but if you cannot solve the general problem of complex mapping from optimized to unoptimized.
Oh, but see, you're trading that off. That's one of the trade-offs. You're saying, yeah, we're losing a little bit of performance, but it's fine.
Well, I want to dig in here because the reality of C++ is that if you train on truly unoptimized code, you'll get a meaningless profile. It will bear no relationship to what is actually hot after optimizations, and so you lose almost all of the benefit of PGO. And we've actually looked at that, especially in very C++ heavy constructs like LLVM. Sometime you should look at how much time is spent at LLVM 0 inside of cast. It's like 30% of the entire execution of the binary is inside of cast. Right. That's not what we need to optimize harder.
Okay. When they say -0, maybe I didn't mean all the way -0, maybe -01 or something. But I get your point. I totally agree.
My suspicion is that we're going to trade the complexity of mapping for the complexity of finding this balance point between enough optimizations that the profile matters, but not too much so that we can actually still reconstitute it. I'd much rather tackle the first problem because it solves we actually get to solve more things with that.
Right. So I fall for that because I tried to do this, and then 0 is mostly like C++ boilerplate anyway, and you said, not this, and then everything else is like 1%. So it's.
In both your techniques, you can obviously identify hot methods. Do you have a technique to measure call graph information about who's calling whom under what scenarios?
Yes. With sample profile, you get.
So do you take a stack trace at these sample points, or how do you?
No, you just use the locations that the hardware counters were in, and so you get your particularly if in your say perf you enabled LBR, the last branch records, you can get call stack information from the profiler.
Okay. Great.
Yeah, gives you free call graph analysis.
Free.
Well, yeah.
In the beginning of the talk, Bob mentioned that the profiling results are stable from run to run. This is not 100% true because you have races on the counters, unless you do locking of thread local counters. So how is it important to have 100% stable profiling, or 99% is okay?
Yeah, you're right. I was fudging that just to make the contrast to the sampling, which is a much more coarse-grained. It remains to be seen, I guess, as we get some experience with this. My intuition is that for what we're using it for, it won't matter if we miss a few counts, but we'll see.
But once you get to global instruction scheduling, that would be critical because you'll schedule your code according to those profiles statically. Think VLIW targets.
Just another quick question. So does the current profiling framework have any way of handling profiling, like how a function returns? I'm thinking specifically of functions that throw. So if you call a function that throws an exception, I want to know how likely it is to exit via that path.
The exception is just a branch as far as the sample-based profile goes. I would assume that the source code can map it, like exceptional edges, and we also do we model exceptional edges in the static heuristics as well.
Okay. But it doesn't look like a branch, right? So there's a way of getting that.
It doesn't look like
it
doesn't look like a branch in the IR, and we don't have a way to annotate it because so far we've seen no interesting programs where the static heuristic is wrong. If we get programs which are where the hot path is throwing an exception, first off, they'll never be optimized well by LLVM because.
Fair enough.
Second off, then we can actually add the annotation if we need it. We can add more annotations when we discover places where we actually need them.
So Chandler, you made a comment about inlining and how we don't know if this is going to benefit because we're not optimizing for call overhead.
No. I didn't say we don't know if it's going to benefit. We don't know how much it's going to benefit. In particular, I'm somewhat worried that the only thing we're going to be particularly good at in the inliner in using profile information is preventing inlining into cold regions. And I suspect that the thing that will help hot regions more is outlining the cold regions around them so that we essentially get partial inlining.
Okay, even if you don't do that, just the fact that we're missing out on the simplifications now because we have arbitrary code size thresholds, that problem goes away.
I don't think we're going to be able to effectively remove the code size threshold based on hotness.
I actually have another one. And the hope I have is LTO in particular and cross-module inlining. with sample profiles, you get cross-module inline information for free, quote.
Sure.
Free. So when you read the profile, you can detect cliques of functions that are calling each other from different files even. So you can decide to coalesce all those IRs together and tell the inline here.
But to go back to Andy's point, there are kind of two potential roles for an inliner, right? One of them is trying to flatten the CFG, like the call graph, so that you don't have calls, which are particularly slow forms of branches, in hot paths. The other one is exposing simplifications, like interprocedural simplifications. From what limited times I've actually looked at this, at least in our code, I see very few places where we would have a hot profile and we would benefit tremendously from simplifications due to inlining. Almost all the places where we see simplifications, we either already get it or it's insane. We would never do the inlining no matter how hot the profile looked because it bloats the code too much. Right? That's my fear. That's why I'm looking a lot more at things like partial inlining, which are much less, have a much lower code size impact.
We over time. Well, thank you very much.